Voy a poner con llave, pues, está en vivo. Vale, si tenéis cualquier incidente o lo que sea, avisáis. Seguridad y está. Vale. Muchas gracias.
Normally you would get a bottle, but Moshe isn't here.
So that's okay. Yeah, perfectly fine. Okay, thank you, guys. And I can see that they are almost.
Yeah,
Really, no?
okay.
Yeah.
Yeah, it looks good. Yes, I think it. So we're probably for next summer.
Next summer. Yeah.
And,
Next summer.
yes, yes.
But 25, no? Or 26?
No. Next,
26.
yes. So
Okay.
Okay, no. So it's promised for early next year or end of this, so that we were starting to plan to be using it in summer. I think there is kind of still, once the building is finished, still several months before one can.
Because they need to work inside.
Work inside, and also there has to be some certification apparently that it's safe to use. So I think this summer the building should be.
Yes, yeah, right.
Usable.
Well, that's the goal, no?
Yeah.
Very good. And what's going to happen with this building? Will it stay
I
remain?
don't know. I think the plan is, yes. So we have right there. I think we rent spaces in a couple of places, so people move in and fill this. We want to rent our labs that are rented on Miramon. I think they should be here. And people in the Camarin Cuzco, I think even some people who are in Bilbao, they belong.
Okay.
And so I think it's not. I haven't heard of any plans to remove these buildings. I'm sure that I would expect that people are changing. Right? Maybe the director will not stay here but move there. But I haven't heard any plans. I'm actually not so certain if I would want to move in the new one or not. One has to see, right? I think the rooms here are pretty nice and spacious, fully isolated.
Yeah.
But so let's see what they.
And what's the size of the building in terms of?
It's apparently our surface area. That's what they. So I don't know how the square meterage, but they were saying that it's about. As much square meters as we have already now in this home.
And that reflects on the number of people that.
Yes, so I think so okay, part of that is of course labs, which is something we don't have. So and then there are things like a bigger lecture hall, and I think also we have right now only one seminar room, and that's too little for. So there are, some of the space will be these communal. And I don't think that I know nothing about this. I don't think that the plan is that it's foreseen that the numbers of employees will double or will increase by an inordinate amount. I think we have this maybe one fellow professor per year is above limit if we get it and so on, but not more, and then that they come. Normally together, PhDs or postdocs. Yeah. So I think this is sort of the. It could be that this still will be foreseen, and that's why I think the first year we expect that some rooms may be used for guests. For example, I think this is also something how we went in Miramar, and many of the long-term visitors that we have to. Go there, and that's kind of it defeats the purpose of it of being incorporated. Yes.
In Myanmar,
yes, yes. So it's a nice place, but it's I think a big shared office. So and then I think people are not really making that much use of it. So I think I also had some. First first there, and they try to be here, or they work from home. And it's somehow not
idea.
Yeah, And so I,
among this.
yes, yes. And I mean, this, right, this was literally the only guests that were not employees. It's an institute built on. Visitors. Probably 15 people who say.
Kind of spend the time with collaborating.
So how's everything going at Fernando?
Good. Yeah, I mean, it's early days because it has to arrive September when I joined. So, there's not much going on, waiting for the tower to be built. So I don't know if you've seen, there is now a construction site next to
Another one.
Good to see you. How are you? Yeah.
I'm fine. Good to see you.
So last time, actually, in February, we took the whole room. Because I didn't manage, I sent the thing to the list, but the list was moderated.
Yeah, and, no, but it was also that I maybe late on Thursday. I was.
Hello, Fernando, ¿qué tal? Muy bien.
Yes, this time.
I have
this
answered
time I'm okay.
Ayer estamos, you're okay, yeah.
But I was out for a week and a half with flu A.
Terrible flu.
I had the winter school the day before in Anadolu. I took everything I could. I gave a talk, and then I went
And you collapsed.
died. So I could not come here on the Friday.
All of you.
I said it often, then that was solved. I kind of, I just, okay, talk doesn't happen, I don't have to worry. I never even checked whether the mail. Also,
I have just replied to you. I don't know if you saw it. I will, yes.
Is this good?
Wow,
Yeah.
the letter is very good. I hope I'm chat GPT or what is it?
It's a colleague that is very good with ChatGPT. It's amazing.
It's wow. All this, yeah, it looks very good. Yeah, I will say.
Yeah, but change whatever you.
No. So the logos, the only thing I have to put is the logos on, but yeah, you will get it today or Monday.
So ChatGPT was not that one.
No, it's perfect.
No, thanks for that. Yeah.
There was a whole session at the March meeting of invited talks about ChatGPT.
Really?
Using ChatGPT for large
science.
language models.
No, but but now it's a language model. Now you said, well, please do a program to split in spherical harmonics. I don't know, like, in Fortran. No, and now in Python and
Yeah, not bad. Not bad.
There were people doing chemistry with a language model. So they were putting molecular sequences.
Todo bien. Estoy bien. Yeah, we were talking about
I remember.
Yeah, I only announced it on Thursday night, you know, so they got that. Honestly, if I would have come, APC would have more room for the. Yeah, it was a strong from the kids.
Is everything fine?
Yeah,
You are well installed?
Yes, drilling next to the
so you were saying you built another, or it's
so
part of the Nanoguni building.
yes, so
Lots of noise there.
There's no parking.
So you get power for yourself.
The worst part.
In the parking.
There's no parking.
No parking for.
No, I mean, it's a bit of a problem. People have to take a family and kids somewhere and then come to Laguna and there's no space. Hopefully we'll only do 3 months while the rest of the building and then people can go under.
Yeah, they said that the parking is going to be closed for much less time than the couple of hours.
So then people don't take it.
Only a little bit.
But
We'll be neighbors.
Yeah.
I'm living in Mallorca.
Yeah. So we were in Talent House at the beginning. I have 2 kids.
Yeah.
Okay, but the kids need a lot of space. So now we want to have Somewhere else, it's more spacious. So that it's a lot of it.
Nice name.
Yeah,
Thomas.
Hopefully get it done today.
So we were talking about the lithium that we are planning to have it by summer.
Hopefully. I mean,
So people already working there.
yes. So let's see. I mean, according to the planning, it should be finished by the end of the year, this year. And then sometime maybe the practice. So it's late spring of this year. That will be hopefully, unless there are some kind of unexpected catastrophe. The way that I hope it's not.
I guess that
So far, I mean, just like a 2 weeks delay or
Es que se hace contar este módulo técnico regular. Está bien.
But the most difficult part, the race is on.
So the foundations are the nonsense.
They were
Is it specially designed for low vibration?
let's say the labs in the ground floor, yes.
So you have a thick layer of.
Yeah, so which is also isolated from the rest of the structure. For this team.
Maybe they are not trusted.
I'll be trying the first time and then. Yeah, because it was pretty crowded last time, so. Sorry, become in favor.
Venga, anda, descargas. Bien, habrá que decir. Esa es la expresión básica. Las personas de bien habrá que decir. Habrá que decir que we are obliged to say that. You want to sit down here?
Okay, good afternoon and welcome to today's IPC seminar. It's a great pleasure that we can now have the talk of Fernando Gonzalez, which had to be postponed from February. Let me say a few words of introduction. He studied physics in Zaragoza, then went to Cambridge to obtain his PhD at the University of Cambridge there, joined Hitachi Labs, where he worked for many years, rising to the position of head of quantum computing in Hitachi Labs. And then he joined a quantum startup, Quantum Motion, in 2020, where he's still working, which is planning to sort of put quantum technologies to work in silicon technology. And there he's principal quantum engineer. And since 2024, he joined Nanogune as a ICABASC research professor. And so that's the great opportunity we have to hear him talk. He's worked in quantum sensing, quantum technologies, quantum dot physics, and today he will talk about quantum computing and silicon technology. So thank you.
Thank you, Geza, for the introduction. And let me start with an apology from the last attempt of me giving a talk. I had a terrible flu A that I picked up on the day before. So if I would have come, you will be all sick. So, but anyways, apologies. No. So, well, first of all, to say that it's early days for me in Donostia. I came in September. So a professor at NanoUne with the objective of doing R&D on silicon-based quantum computing. Okay. I will be speaking with two hats today, not only that of NanoUne, but also the hat of Quantum Motion as head of quantum hardware development, because also the company is coming here to Donostia to establish an R&D laboratory that will not only serve the activity here, but in the European Union. So it will be the hub for the Union. And the decision to come here is because there is an excellent ecosystem for the development of quantum technologies that you can see outside the region. It's making a lot of noise. People are getting attracted about what's going on here. And Quantum Motion was one of the first to decide to come to the region. Good. So before I start with the details of the talk, I wanted to tell you what happens in my mind, particularly when thinking about computing, and particularly next stages, more powerful computing. No? And people, when posed with this question, they will think of high-performance computing systems, supercomputers. That's fine. Some other people will add the picture of Jensen Huang from NVIDIA coming up with a massive wafer with I don't know how many of the AI cores that they can fit in there, but a good number of them, as you can see. So yeah, of course, this is a direction towards more powerful computing, but what's in my mind, it's slightly different. Okay, so when I think of more powerful computing, I think first of all of quantum computing, and particularly utilizing silicon technology, a technology that we believe can take us to a paradigm in which we will be able to integrate on a single chip qubits, but also classical electronics, because quantum computers will be systems, quantum computing systems, that will not only contain the accelerator, the quantum processor, but will also have classical electronics embedded onto them. So having the possibility to have all that together on a single chip at low temperatures in a dilution refrigerator where these solid-state systems operate better, it's very appealing to me. So that's why I work in the area, and that's why I want to present to you today the concept itself. Good. So in terms of the outlook, I have a number of things that I wanted to tell you. First of all, about the group in NanoUne and Quantum Motion. Also talk about quantum computing and the vision behind utilizing silicon, the state of the art in the field, and then going into the new era of the topic, which is industrial manufacturing and the results that we are obtaining in Quantum Motion and in the group. Good. First of all, on Quantum Motion globally, say that it's a startup focused on developing silicon-based quantum computing hardware, and it has several areas that we cover. The one that I lead is that of the quantum hardware itself, where we are going to be talking about spin qubits, and particularly spin qubits in silicon quantum dots. But we also have other domains of research and development, which are cryogenic electronics, device modeling, intelligent automation techniques for tuning up quantum processors like ours, and also theory, particularly on development of quantum algorithms that are aware of the hardware that they are going to run. So they take into account the restrictions that physical hardware is going to have. Good. So all these activities, in principle, will be happening here in Donostia as well. But just to give you an idea of the size of the company nowadays, we have several teams distributed on several areas of work. The most sizable team is that of the quantum hardware, which I lead. Now we are even more than this. And then it's also remarkable to mention that we have people that have come from industry, integrated circuit designers that have worked for Texas Instruments, Qualcomm, that are excited about the topic and they want to make a contribution. So they move from these big companies to to work on quantum motion. Good. And to give you an idea where the company is and the size in terms of equipment, it's in central London, very close to King's Cross. People are welcome to come if you would like to do so. And then there are a number of dilution refrigerators that we utilize for our experiments, up to 9 in April, and also for Kelvin systems, test benches, workshops, and collaboration spaces. Good. And the company starts to be more and more distributed. It started in London around UCL, but also with founders from Oxford, collaborators from the University of Cambridge. We also have collaborations with the National Physics Laboratory and now with the National Quantum Computing Center. But very recently, we have established a collaboration with the University of Pennsylvania and then also opened a facility, a measurement facility in Sydney last year. And this year, hopefully, around September, October, we will be opening, Quantum Motion EU will be opening in here in Donostia, next to or inside the facilities of Nanogune, which you can portray here. You can see that over the course of the next months, this tower that doesn't exist at the moment will be built next to the facilities of Nanogune. It will be an extension to the center, which is going to be the host of my team, the Quantum Hardware Group at Nanogune, and also it will be the host of Quantum Motion Spain. So it will be an intertwined collaboration in which we will be doing R&D on quantum hardware development. It's a 7-story building, and at the beginning we will be enabling 2 floors of that building for offices and lab space. Particularly in terms of laboratories, from day one, we expect to have 2 last generation blue force dilution refrigerators, as well as 4 Kelvin testing systems that we utilize before we go into the measurement phase at millikelvin, and also high frequency electronics. Good. Feel free to interrupt me at any moment if you have questions, but otherwise I'll go into the topic itself, quantum computing and hardware development. Probably this type of slide you've seen a million times. What are quantum computers good for? Well, they are good for a number of topics because they utilize a different paradigm with concepts from quantum mechanics, such as the concept of superposition and entanglement that have no classical path. So with resources for computing like those, it's been theorized that quantum computers will be very good at factorizing large numbers, which is essential for online security. They are particularly good at database searches when the database is unsorted. And also, they are good for optimization problems, as we are starting to see that can be utilized in the financial sector, weather prediction, you name it. No? But the topics that excite me most as a physicist are those 2 that are related to the simulation of new chemicals, new medicines, new materials, and particularly quantum computers are known to be very helpful once we have a sufficient scale. And in terms of scale, we can discuss how the evolution of quantum computing is seen in the community through different phases of development. Particularly, the quantum computing phase that we are now is typically called that of noisy intermediate scale NISQ, the quantum, in which the size of the quantum systems, the quantum computers that can be built are relatively small, so of the order of tens or hundreds of qubits. But in order to run useful algorithms, the fidelity of these systems needs to be excellent. So we are going to be talking a lot about fidelity, so the precision through which you can perform operations. So you need to have errors on the order of 10 to the minus 4, 10 to the minus 5 every time you try to perform an operation. So this is where we are. Error mitigation techniques are pretty useful in this era because we have no error correction at the moment. And also in this era, it is known that you may run operations in parallel if you were to have a number of these quantum computers, not just one, but a number of them, because, for example, variational quantum algorithms are particularly good for this sort of parallelization. Good. But I think the community also starting to see that the most commercially relevant problems and also societal problems are going to need of quantum error correction to be run. Quantum error correction comes with a requirement, which is that in order to have a computational qubit, you're going to need a number of physical qubits of the order of 1,000 or so per 1,000 physical qubits or so per logical qubit, with typical error rates that we find in systems nowadays. So in order to have to be able to run some of the most complex algorithms that we've discussed, the target is in systems that will be able to scale eventually to the millions of qubits. So that's a very demanding requirement, but that's one of the targets of the community. The benefit is that the systems don't need to be that excellent in terms of fidelity. You see that we can trade off error rate for the number of qubits to be able now, in this case, correct for those errors that are going to occur in the system. Good. So if we take into account that quantum error correction is going to be essential, we need to think of codes that implement that type of error correction. And the most common that people are thinking of and try to implement is that of the surface code. Let me try to explain briefly. The surface code requires a two-dimensional array of qubits, and in this case, the qubits are represented by white and black circles. The white are computational qubits. The black are error-correcting qubits. And the ellipsoids that you see there are operations that are performed between qubits, particularly control nodes operations. And we will have two types of errors in the quantum domain, not only bit flips, and for that the set parity qubit will take care of looking at, but also phase errors, because we have the quantum mechanical phase, and we may have quantum errors on the qubits that will be monitored by the X and Z. In any case, you need to build up this two-dimensional array of qubits in which you will alternate data and ancilla qubits for error correction. And that imposes quite a lot of demands on the hardware that you're going to utilize to build such a machine. And to me, something that comes to mind, we've discussed this, no? That we need this two-dimensional arrangement with nearest neighbors couplings and classical electronics. But to me, this resembles quite a lot something that we've already seen in technology, which is very much a silicon CMOS image sensor. So this is what you have in your phones, in your cameras. This is a chip that contains a number of repeated unit cells distributed in a two-dimensional arrangement. These are the pixels. And it is integrated with classical electronics. There is a readout and addressing electronics placed at the periphery of that CMOS image sensor. And nowadays we have cameras with more than 100 million pixels in the size of your fingerprint. So that's what encouraged me to look at silicon, no? Because even if we look into the pixel, we can see some symmetries between a diode, a pixel, and a qubit, where you have the location of a photodiode. You could visualize that as the location of your qubit. And there's already some distributed classical electronics in the proximity of that qubit. So if we inspire ourselves in this paradigm that is being used in CMOS image sensing, we may be able to construct that array of qubits that is required for the surface code, the quantum error correcting surface code. Good. So putting all together, the vision is to go from these distributed machines that we have here. This is one of the most famous quantum computers, the 2019 Google's quantum computing system, Sycamore. the one that was utilized at the time to claim a quantum advantage for the first time. It's a chip that is somewhere there at the bottom of a dilution refrigerator, and that is connected by hundreds of wires from the bottom of that refrigerator to room temperature electronics. And you see the vast number of cables that are utilized, the large number of room temperature electronics that is needed. And this is effectively a distributed system, no? That resembles some of the first computers that were built at the very beginning. No? And the vision is that, no? Try to put as much as possible of that room temperature electronics in close proximity to the quantum processor, such as we move from distributed systems into integrated quantum computing systems that contain as much as possible the cabling and the room temperature electronics that is needed to drive quantum computing systems. Good, so that's why I think silicon is great, but there's a lot of work to be done, particularly silicon and transistors in silicon processes are not qubits by definition, but they are close. And what we do, and my team does, is adapt modern transistor manufacturing processes to enhance the quantum functionality of those devices. So very briefly, how we do that, we think of, for example, one of the latest Apple's processors that contains more transistors in the size of your fingerprint than people on the surface of Earth. And we look closely at one transistor. This is how a TM image of one of their transistors may look like, in which you have a source, you have a drain, and you have a gate. And that is going to control some current flowing through that channel, depending on the potential that is applied to that gate. So with modern transistor nodes, that gate is less than 50 nanometers or so. And then what we do to modify the operation of these transistors is cool them down to low temperatures, typically below 4 Kelvin, change slightly the geometry of this gate over the silicon channel to isolate individual electrons under the gate region. So this is effectively an electrostatic potential created by the gate where we confine individual electrons. And then if there's a single electron or just a handful of them, applying an external magnetic field will split its degenerate levels into spin down and spin up. And this is typically the qubit that we will be utilizing for our purposes, which is the spin of a single electron trapped in an electrostatic potential created by a metal-oxide-semiconductor nanostructure. Good. So this is from a technical point of view, fabrication point of view, but it turns out that silicon spin qubits also have extraordinary properties as qubits. For example, their coherence time, T2, that is seen as the quantum memory time of these systems, is one of the most coherent of any solid state system in nature, with T2s of the order of 30 milliseconds or so. This is, for example, comparable to the reference time of dynamic random access memories today. And the other is that silicon spin qubits can be operated at elevated temperatures. And when I say elevated, I mean a Kelvin or so, as opposed to tens of millikelvin. You may say, well, this is not a very high temperature anyways, it's not elevated. But it turns out that you can get substantially more cooling power at 1 Kelvin than the one that you can get at a few millikelvin. And that helps if you are thinking of building a large-scale system with classical electronics dissipating heat as it operates. So that's a good advantage in terms of available cooling power at that temperature. Good. So that's a bit the vision. What is the field at the moment? Where are we standing as a community? So in order to understand where the field is, first of all, we need to understand the technology requirements to build a quantum computer. These were posed a number of years ago by a physicist working at IBM at that time, Di Vincenzo, that said that your technology needs to be manufacturable. So you need to be able to build scalable, well-defined qubits. You need to be able to initialize your system with a success rate of more than 99%. You need to be able to write your information. And in quantum computers, you do not only need to operate on individual qubits, but you need to perform two-qubit gates. And finally, you need to be able to read your information, again, with a fidelity of more than 99%. If you can do that with your technology, you have a quantum computing technology. So let's see where the field is at. First of all, silicon spin qubits, we've seen that they are manufactured with metal-oxide-semiconductor processes. One of them that is very popular nowadays is through silicon-silicon germanium heterostructures. This is, for example, the type of heterostructure and gate stack that teams at the Netherlands, Delft, for example, will utilize. And then you have the pure silicon-silicon oxide metal process utilized by groups, for example, at UNSW, that by posing or placing gate electrodes on the surface of that heterostructure, one is able, by applying the right potentials to those gates, to trap individual electrons, as we've described. Good. So that's how silicon spin qubits are typically made nowadays. In terms of one qubit control, it is done through electron spin resonance techniques, in which a non-zero magnetic field, you split your spin states into spin down and spin up. And by sending microwave signals on resonance with the Zeeman energy for certain duration, you can see how the probability of finding a spin in the up position changes over time. These are Rabi oscillations of the single spin system as measured as a function of the duration of that pulse. And researchers have been able to achieve fidelities of these single qubit gates with more than 3 nines, nowadays 4 nines even, and at rates of 1 to 10 megahertz. This can be seen as the clock speed of the quantum process. For 2-qubit gates, typically the spin-spin exchange interaction is the one that is utilized. So that's a short distance interaction, such as if you can control the separation of those qubits, you can control their exchange coupling. So through exchange interaction, 2 types of gates have been developed: the control rotation, which is a frequency selective driving, basically ESR, but with exchange on, and fidelities of more than 98% at a megahertz have been achieved. The control phase is basically turning on and off the exchange for a period of time, and with that, even better fidelities have been obtained of the order of 99.5, and nowadays even close to the 3 nines. This can be fast because the exchange interaction can be strong and be done at 10 megahertz or more. Good. So with those ingredients all put together, the field stands at a relatively small scale, I would say. Because if we look at the literature from 2022, particularly, several groups across the world demonstrated 2-qubit quantum processors with fault-tolerant fidelities. So all the operations being performed above 99%. So still, these are relatively small systems, but they fulfill all the criteria set up by Di Vincenzo. Also, in that year, a small 3-qubit quantum processor was operated in Tokyo, and the first demonstration of quantum error correction was implemented on that one, particularly the phase split. And the community stands at 6-qubit quantum processors nowadays. This is the 6-qubit device developed at the University of Delft, where you see an array, linear array of quantum dots up to 6, with charge sensors on the left and right side to read the state of those qubits. Although it's a 6-qubit quantum processor, the maximum entanglement that was achieved on that device was of 3 of the qubits at a time. Good. So relatively small processors compared to other technologies, but their specifications look particularly good at the small scale, I would say. So here I wanted to put a comparison, for example, between the initialization gate fidelities of silicon compared to those, for example, of nowadays relatively old IBM Heron with medium fidelities set up here. So you can see that silicon spin qubits may be competitive, particularly at the single qubit gate level, but there's a lot to do, particularly on 2-qubit gates. When operating complex systems like this one with 6 qubits, the 2-qubit gate fidelity drops to around 95%. But one of the major benefits of silicon technology is that readout fidelities can be particularly high compared to other qubit technologies, and that will be essential moving forward in terms of quantum error correction, in which you need to be reading all the time, basically. Good. So moving forward, you've seen small-scale quantum processors. Those devices were typically manufactured in academic university clean rooms. Now there is a change in paradigm in the community, and those devices start to be manufactured in professional clean rooms, such as those by IBM or Intel. And particularly since 2016, devices that follow manufacturing processes of the semiconductor industry can be made and used for spin qubits. So we have the first demonstration at Leti, then IBM, and then afterwards Intel, that pushes very hard on this area. And also, since then, there's been a number of demonstrations showing that quantum dots and qubits can work together with classical electronics. For example, myself back in 2020, and other people using the 28 nanometer node, for example, and people thinking how that quantum computer may look like once we build it up into a more complex system. For example, a quantum computer proposal from us in 2023. Good. So with that, I think I covered a little bit the field. So I hope that introduces you to the topic of silicon spin qubits. And now I would like to move on to the results of my team, and particularly an explanation of our approach. Please let me know how we are doing with time, such as in case I need to accelerate at some point. Good. So the approach that we follow is to utilize industrial fabrication processes, because we don't want to have just a handful of qubits. We want to build a system out of this with the objective to enable this large-scale integration and integrate classical electronics as well. And we follow two paths at the moment. One is we utilize IMEX 300 millimeter line. Some of you may be familiar with the RTO in Belgium that is coming to Spain, actually to Malaga, with a large manufacturing facility. And we utilize one of their experimental processes, the multi-gate MOS process, that allows us to construct devices in a bespoke manner. We can do almost whatever we want with this process. But also, we come from the other side, completely the other side, which is utilizing a process that is fit for classical electronics, is in industry, is the 22 nanometer node global foundries process, and we try to adapt it as much as possible for quantum functionality. Particularly, this is great because all the analog digital electronics works well, and it works well at low temperature with some modifications, but it works. Fortunately, I have time only to cover this part, so let's go into it. With this type of technology, at the moment, our approach is to build scalable unit cells. We want to come up with a unit cell that can be repeated as many times as possible to construct that large-scale quantum computing system. And we use, at the moment, a bilinear topology in which we have qubits distributed in a sort of ladder configuration, and we have sensors, readout sensors, placed in different locations of the unit. This is all done in isotopically enriched silicon to guarantee long coherence times. Good. And what I wanted to discuss today is some results on high fidelity readout that we can achieve on those devices, our 2-qubit gates mediated by exchange, and our high fidelity single qubit gates on systems of up to 4 qubits. And why up to 4? Because over the course of this year, we are delivering a 4-qubit system, so relatively simple, but of high specification, to the National Quantum Computing Center in the UK, in which we will be providing our technology built in such a way that is scalable, such as we don't stop at 4, we can grow to larger quantum computing systems. At the moment, this is a scalable linear array, that's our unit cell, that can grow to more complex unit cells. Good. So let me guide you through what we do. So this is an SEM image from a device made at IMEC. Particularly, I'm going to try to explain to you how silicon quantum dots and silicon qubits are made on this technology. So these are gate electrodes that have been placed on the surface of a silicon oxide interface, and the different electrodes have different purposes. But for example, this electrode there with P1 and P2 are gate electrodes that are utilized to form the quantum dots at those locations, and a reservoir of electrons from where the spins are going to come to populate those quantum dots. They are going to be hosting individual spins. For that, you just need to apply the right voltages to those gates to create this electrostatic configuration. Then, typically, the community would have another quantum dot in close proximity to the computational quantum dots as a charge sensor. This is typically known as a single electron transistor. And it has some caveats that almost eats half of your space in the processor. So we've been working quite hard to get rid of it and sense differently. The good thing is that these type of sensors are very high sensitivity and provide fidelities without too much hassle of 99%. So what I'll be showing you is, first of all, how we get rid of that sensor. And what we do is use the same gates that are used to control the quantum dots to sense, giving us extra space to put more quantum dots and increase the connectivity between them. And doing so with high fidelity, although until now the community had trouble getting to fidelities of 70% or more with this approach. Good. So starting with the readout in our linear quantum processor that we have here, I'll show you the demonstration done by one of my students, Constance, on a bilinear topology utilizing dispersive charge sensing techniques. So we are going to have our two quantum dots that are going to be interacting and our sensor placed in a bilinear topology, which is going to sense particularly the charge state of Q0. A bit more on how the gates are deployed on that device. So you have gates that create reservoirs and gates that create those electrostatic potentials where the electrons are going to be placed. This is, for example, for the sensor side, and that gate stack is for the qubit side of things. Very importantly, we have also gates that control the tunnel barriers. And this is essential, for example, to control the couplings between the quantum dots, but also control the tunnel rates between the qubits and the reservoirs, or even the sensor and the reservoirs. Good. Basically saying that this is a fully electrostatically tunable structure that allows to control qubit sensors and their tunnel rates. Good. How do we sense? So we have a special technique for sensing the qubit state. Particularly, we will connect an LC resonator. This is where it becomes very much an electrical engineering problem. And this is an oscillator that is going to oscillate at a particular frequency. This is, for example, the reflection coefficient of that LC oscillator as a function of frequency. And you can see that it oscillates at a characteristic frequency. But when an electron moves between the quantum dot and this reservoir, the frequency is pulled down, and now we have a new frequency. Basically, we transform the problem of detecting individual electrons in detecting resonant frequencies of a resonator. Good. So this is how our sensing is going to work. So we will change the potentials on the gate that controls the quantum dots, TP1 and TP2, you see here and there. And we will record the signal that comes from our sensor plus resonator. And you will get maps that look like this, where we can define specific charge states. Specific charge states that are of interest, particularly the first number indicates the number of electrons on Q1, the second one, the number of electrons in Q2, and the last one indicates the number of electrons in our sensor. Particularly interesting for us is that region in which we are going to move from two electrons that are separated across the quantum dots, or the two that are joined on the same quantum dot, the 1,1 to 0,2 transition. So what's happening here? Why do we have signal? Well, basically, a single electron is going back and forth between the reservoir and the quantum dot because of the excitation of the resonator. And then as we move across the 1,1 to the 0,2 transition, that electron motion stops. We have no signal anymore. And then we know that we are in the 0,2 state. Okay, so at the moment, what we have here is a very good charge sensor, a single electron charge sensor that detects a single electron moving from A to B. Good, so the system as such is projected to the charge basis. Now we need to think about how we convert that charge information into spin information, because we are not dealing with charge qubits, but with spin qubits. A bit on the physics of the two-spin system. This is the eigenenergies of our two-spin system as a function of the detuning potential between the two quantum wells, particularly done at zero magnetic field, where we are going to have singlets and triplets, separated singlets and separated triplets, or joint singlets here. This is the singlet 0,2 state, singlet 1,1 state, triplet 1,1 state. The singlets couple with each other, but the triplets do not couple in this energy landscape. And this is going to be essential in understanding spin projection. Good, so then we apply an external magnetic field, and now our triplets are not anymore degenerate. We have the T minus spin down, down, and the T plus spin up, up, and also the T0. Good, so we have our system prepared in such a way that is going to allow us to perform spin readout. So normally we will prepare the system at this detuning point and then move it to the measurement point to read the spin state of the system. So what happens? That MS0 states, particularly the S11, maps into the singlet 0,2. So we have a charge event happening if you are in a singlet state. It turns out that as you move from the T0 to the readout position, you go to this point, but there is a rapid relaxation onto the singlet state. So the T011 maps into a 0,2 charge state. However, the MS plus minus 1 are blocked for a period of time, such as if I was in a spin down down state, I'm not going to change to the 0,2 charge state. And therefore, I'm going to be able to read the parity of these two spin systems. So how does the data look like? So this is a measurement performed by our resonator as a function of time after we perform the pulse from the prepared position to the measured position. And you can see that we have three potential outcomes. We have a singlet state in which the signal is 0 all the time. That's because the charge transition occurred instantly. However, the most relevant one here will be a triplet minus spin down down state that as we pulse to the measurement point remains in the 1,1 state for a period of time that you can see here to eventually relax and then become a singlet 0,2 state. During this period of time, we can acquire the signal difference between those two states to distinguish whether we had a T minus state or a singlet state, very much being able to read the parity of the system. You can construct statistics on this type of measurements. You perform the same measurement 10,000 times, 100,000 times, 1,000,000 times, and you can see that you have counts, particularly at two positions, and the separation of those two Gaussians tell you about the fidelity of this readout process. Then you can plot your fidelity or infidelity as a function of the duration of your measurement to see that depending on how you tune your sensor with respect to the quantum device and how you tune the tunnel rates of the sensor and the qubit, you can obtain different fidelity profiles. I think the most remarkable here are those that relate to fidelities approaching 4 nines, that are obtained at around 300 microseconds. So it's a long measurement, but very precise. Or if you tune things slightly different, you can have very decent fidelities, 99.5% in relatively shorter time of 30 microseconds. Good. So that's about readout. And then I'll speed up on single qubit gates and two qubit gates. So for single qubit gates, we've discussed already, we are going to be utilizing electron spin resonance techniques. And this is very much what we do. This is an example of our payload. So this is what will go into one of our refrigerators. And particularly, I wanted to highlight that we have transmission lines in our chips that are going to deliver the microwave signals to the QPU. So we are going to be performing single spin rotations via this microwave strip line, basically electron spin resonance at the single spin level. We are going to apply an external magnetic field, and we are sending that excitation on resonance with the Siemens splitting for a period of time. And normally we'll be sending a Gaussian pulse to better control the fidelity or improve fidelity of the single qubit gates. So here's an example of a radio oscillation of our of one of our spins. Particularly, we are measuring the parity, the probability of being in the odd parity state, because we are projecting the system as a function of the pulse duration. And you can see very nice radio oscillations as a function of time with typical radio frequencies between 1 and 2 megahertz, T2 stars of the order of 100 to 100 microseconds, quality factor, the number of oscillations that we get before our amplitude of the oscillations drops by 1/E of the order of 300, meaning that we have single qubit gate fidelities of the order of 99.8, 99.9, so approaching the 3.9 figure. As an example also here, you can see some very nice Rabi chevrons showing that single qubit control operation. Good, and then finally, we have the two qubit gates. So basically, we need to activate the exchange interaction between those two qubits to perform a control rotation between those two. So there are many ways to do that. The one that we are going to choose is that of the exchange interaction that we are going to basically control by voltages, utilizing the voltages on the surface gates. And then this can be fast to the order of a gigahertz or more, producing rotations between the up-down and, this will be up-down to down-up rotation. So basically rotate along this axis in the Bloch sphere of the two-spin system. There are other mechanisms, but we don't have time to go through those. So just to give you an idea of how the pulse sequence for a two-qubit gate works, it's rather complex. You may start in the 0-1 configuration and pulse to the 0-2 configuration to initialize the system. That places you in a nice singlet state. Then you separate the system and plunge into the 1-1 region for a period of time until it stabilizes. But most importantly, you go into the exchange control region here, close to the detuning, the point of the energy between those two states for a fraction of time. Then you come back to the plunge position to remove the acquired phase, and then you go into the measurement point where you're going to perform your measurement. So a number of voltage pulses that you need to perform to eventually produce a nice radio oscillation, particularly in this case, is between the two different states that we discussed before, the up-down and the down-up states. So you see that as a function of time, where here in the x-axis, we have the time that we spend in the J position. Okay, good. You can repeat the experiment at different J positions. This will be epsilon J, as you have here, and then as a function of time. And you can see how you can control the speed of your radio oscillations as you go deeper and deeper into the zero detuning point. Just to give you an idea, at this point, at this one-dimensional solution of the map, we've performed a swap operation. Basically, we've gone from a spin up-down to a down-up. So you can see that this can be rather fast, of the order of tens of nanoseconds, and much faster than the single qubit gates. Good. So with this, putting all together, we can set some specifications to the work that we do, particularly talking about the phasing times. We are very much at the typical literature values of 20 microseconds or so. Rabi frequencies of the order of 2 megahertz, good. Exchange oscillations happening with speeds up to 150 megahertz. And single qubit, 2-qubit fidelities and readout fidelities looking rather nice with 3 nines for the single qubit gate, not yet on 2 nines for the 2-qubit gate, and more than 3 nines for the readout fidelity. So very nice specs for small systems so far. Good. So with that, I give you a very quick, rapid overview of what we do. I'm about to finish the presentation, but I wanted to tell you a bit more of what's next, after this. Of course, we are trying to build more complex systems with higher specifications as we move along. But I wanted to advertise that since yesterday, it is public that we've been selected by DARPA through their Quantum Benchmark Initiative to be one of the companies that is going to be observed by the institution for the next 6 months to develop a plan for utility scale quantum computer, a computer that in 10 years or so will be able to be useful in a manner that will transform society. So this is the first stage. It's just 6 months in which we are going to develop a very detailed plan, working together with DARPA to see our path towards that utility scale quantum computer. And also, during the next year and a half or so, we'll be working with UKRI to implement the first example of quantum error correction in silicon with a particular processor not too dissimilar to the one that I've just shown you. Good. So with that, I think it's time to conclude and say that silicon spin qubits in general are looking as a competitive solution for a scalable quantum computing hardware. And personally, my group is utilizing silicon at the 300 millimeter wafer scale to deliver that scalable quantum unit cell. We are demonstrating all operational steps to high fidelity. And at the moment, we are focused on this 4-qubit system for the National Quantum Computing Center. So with that, I would like to conclude and maybe leave an image there that maybe if we work hard and we make this work, there could be a new revolution, the silicon revolution, again, a revolution that may look familiar. Good. Any questions? Please go ahead.
Thank you very much for a very nice talk. So, in this, let's say, silicon qubits, more or less easy to entangle two electrons, which are fixed or next to each other. How do you want to, let's say, put in entangled states the qubits which are far away from each other? You can do it in a consequent way, or you have some other ways?
You're talking about non-nearest neighbors coupling. So you quite right say that silicon spin qubits are great if you think about nearest neighbors coupling because you have the exchange interaction, short range, it's great. If you want to have more or non-nearest neighbors interactions, there are a couple of things that people have been working on. One of them is inspired on the work that is done with superconducting qubits, which is to couple a qubit to a microwave resonator. That microwave resonator will have traveling photons that transmit the information to another location that may be millimeters away. People have done this, but the fidelities of these long-range links are not close to 99%. So it feels like people are abandoning this idea. Also, because it removes a little bit the purpose of utilizing silicon as a compact quantum computing technology, because you end up having these microwave resonators that occupy substantial space. There is another approach that is much more natural to electrons, particularly, which is shuttling. basically take an electron from one location, put it into a shuttling bus, move it to another location where you will have another electron, perform the interaction, and then bring it back to its original location. This works, and this movement of the spin over micrometer distances can be done to high fidelity. So I think this is a nice way to increase the connectivity, and many people in the field are trying to bring this on board as an ingredient to what we can do. So the term is called spin shuttling. So moving the spin around by physically moving it.
Thank you. I have a small question related to this connectivity. I mean, why is it 1D? I mean, could you also, have like two-dimensional arrangements of the quantum dots?
It's a technological constraint at the moment. So let me try to see if I can explain it simply. So you have these gate electrodes. Maybe I can put an example.
You have a blackboard there if you want, Fernando.
Yeah. But we lost it, no?
Yeah.
Maybe let's give it a go. And I think there is a good image that we can utilize here. Let's see if it comes back. Yeah. So we had the sort of a 1D array here. If we get rid of this, you can extend it nicely. And you have the gates. You see the P gates, they are coming from the bottom. I could have gates coming from the top to make the second line of qubits. That's easy, no brainer. Bilinear array, as long as you want. I mean, not easy, no, but it can be done. So the question is how you put the third line, that now you brought gates from top to bottom. No, that's a fabrication challenge. It's been addressed, and it's been addressed by utilizing the third dimension. So you can now bring more gates from the side, but a higher level, and then they come down, land on this region that matters to you, and then you have another 2 lanes, and another 2 lanes, and another 2 lanes.
And that would be the way of scaling everything up, or
Well,
in principle, you can also scale up a 1D system. But
So there are 2 perspectives. One is, okay, more connectivity, the better, but we need to wait until the technology is there to create these more than bilinear arrays, but it will happen. The other is, with bilinear arrays, we can run the surface code, and we have a paper on this. So you can map the surface code in bilinear arrays. You can do quite a lot on bilinear arrays, no? So the other thinking process is, what do you do with what you have today, no? And how you run things efficiently, given that you don't have all the connectivity that you would like. No?
Okay, I have a question. You were pointing about the fact that the first computer had a lot of quantum computer had a lot of cables that were going out of the transistor and then to decrease the temperature to correct to the room temperature. Why is in this approach you are going to lose this? And this is not clear to me.
Yeah. First of all, one is to question what's here, no? What do we have here? There will be arbitrary waveform generators, microwave sources, digitizers. There will be mainly that. Then all this cabling is just one cable that continues all the way down to your processor. So you have at least one of those cables per qubit, if not more, 2, 3 probably. So you don't have any form of multiplexing. It's just n or prefactor n number of lines, n being the number of qubits. There are a number of things that you will be able to integrate on a chip. I mean, more specifically, no, you can shrink all this that you have here into a chip that occupies the size of a fingerprint. I can have a microwave source that doesn't occupy more than this.
But then you will have always some cable that needs to go out of the cryostat to your electronics. So
No, it can sit on the same chip as your silicon spin qubits, for example. The biggest challenge is not to put them together. The biggest challenge is to design the electronics to low power consumption specifications. Because I can put a microwave source here and qubits together. The only challenge that you have there is to run the microwave source in such a way that doesn't dissipate too much power, that it heats up your chip and the dilution refrigerator above the specification temperature. But physically, there's nothing stopping you from doing that. It's a challenge for low temperature electronics. And that's why people from industry are coming to work on this area, because they see a challenge and they want to solve it. No? That of designing known blocks that are here to low power specifications compatible with dilution refrigerator.
okay, this is clear. But anyway, we need to talk with this object that is in the cryostat. So we need to have anyway cables coming out.
But then you can reduce substantially the number of cables that go to your chip, because
Okay, so it's just a reduction in complexity.
Yes,
Cables that are used.
yes, just a handful of low frequency cables to program it, and then you go.
Fernando, a little bit more on the interconnectivity, and when you scale up and you try to go from 5 to maybe 10, 60, 100, on top of the connectivity, you have also a topography problem, right? Of the design when you go to very large circuits and you start scaling really, really up. What would be the roadmap for topographies? I mean, we know these hexagonal networks that they are being produced. What is your roadmap in that topography of qubits?
Yes, so the way we see this working best is we talk about these bilinear arrays. It will be bilinear arrays that are joined at two-dimensional junctions, creating a sparse 2D arrangement, leaving space in the middle of those loops that you will be forming for routing, for on-device level electronics, you name it, no? But it will be a sparse 2D connectivity. I can send you a paper in which this is nicely laid out, but it's literally this, bilinear arrays that are joined at junctions with 2D connectivity.
One more.
Thanks for the talk. So you mentioned as far as a long-range coupling, moving towards shuttling in favor instead of coupling to photons. This has worked well for superconducting qubits, as you mentioned. Do you have an idea of why it's not working so well with silicon? I mean, is it a coupling strength issue, or is it noise?
Coupling strength is weak, so the dipole of our qubits is smaller, typically, than the dipole that you have in superconducting qubits, making achieving the strong coupling regime hard. It's always been historically hard for silicon spin qubits. And also, fabrication-wise, is a nightmare, because you are trying to fab a high-quality resonator on a semiconductor stack, and you get quite a lot of losses once you put your superconductor on top of a semiconductor structure. So many times you just have to get rid of all the semiconductor and have the small mesa where you have your qubit, and everything else is your superconducting part. No, so in short, no, a fabrication nightmare. No, it's one of the other challenges.
Okay, I think a lot of questions, and Fernando is not far from here, so he will be happy to answer more questions. So let's thank you again.
Bueno, Fernando, pues muy bien. Muchas cosas. Son aspectos. Yo creo que la gente no termina de entender. De la ventaja grande de todo esto. Sí, sí. Que te han preguntado y dice, bueno, estaba claro. Sí. Bueno, yo te dejo. Vale. Hablamos, te mando la carta.
Muchas gracias. ¿Sirve el lunes, como muy tarde?
El lunes, sí, por
Vale,
favor,
pues
porque mando el martes la propuesta.
Bueno,
Es una
si no,
cosa
si
de...
puedo esta tarde, te mando esta tarde.
Es una cosa de invest.
Ya lo he visto. Suerte.
How are you? What's your name?
Max.
Max. Nice to meet you.
Writing here low temperature laboratory. We just started, let's say, and now
This is
because I think you organize
Yes. The other day I was walking around and they saw me from the outside your
Yes,
yes, I love it. Yeah.
so now it's open and we have some records besides entering, let's say. My background is material science, so we developed, let's say, heterostructures to get spin split density of states.
It's another interesting talk today.
I came directly from
This was also different. Sort of a slow start. It was not so much.
with any form of Majorana.
Well, for us, it's more
Better to have an excess than not.
But
Audience dilutes over all
what's
the
interesting is
Yes.
collaboration. We cannot help much, but at least we have.
unless there are positions where you're being paid for
The best will be that I come live one day.
So if they want to ever, then I think
If you have a short presentation on things you do, and then I listen, and then because normally
That's what here, right?
if I hear you speaking about what you do, then maybe some ideas will come to my mind. Oh, how we could collaborate.
So maybe I don't know, find something.
Yeah.
I cannot do anything like this. So we basically have no fabrication. So we
But I'm very keen to understand what's going on in the region, what the people that
okay, but if
we
I
can
think
work
of
together
myself,
with. Because
how far away chemistry was
of
from
course, I mean, I don't come here to be
I'm not surprised.
I'd very much rather
Centro Nacional